Video, we're going to go over the derivation of discharging a capacitor. All right, let's begin. So let's first start off with the charging of a capacitor formula that we derived last time. So this is the charging up. We found that the function for charge per or charge with respect to time gave us the capacitance times the potential difference 1 minus e to the negative t over RC as the function for a charging up of a capacitor. And for this one, we had a EMF source connected to a resistor R, and then we had a capacitor here, which we could call just C. Okay, so we're actually going to start off from this diagram, but before that, I always like to show where we're going to end up. And so the discharge, we have Q of t is equal to Q naught, which is the initial amount of charge of the capacitor, times e to the negative t over RC. So you can see that it looks very familiar with the charging up, but the discharging here, the e to the negative t over RC doesn't have that 1 minus, and that 1 minus does give us different graphs, and I'll point that out later. Okay, so the first thing that we did for the charging up, we looked at the schematic and we figured out the direction of the flow of charge. And so this time we're going to do the same thing, where we know that this is a positive plate here and this is a negative plate here. So what we found out is that as the capacitor is charging, the plate closest to the positive terminal of the EMF will become positive, and the plate opposite of that will, of course, be negative. And so the flow of current would go in a clockwise direction, like so. Okay, so we have current flowing clockwise. All right. We also made Kirchhoff's loop rule, and we went with the direction of current. So we also said the Kirchhoff loop was a clockwise loop. Okay, so the reason why I want to start off with this schematic here is because for the discharging, we have to use the same idea. But here's a couple of very important things. When we discharge the capacitor, we want to remove the EMF source. Okay, so when we remove the EMF source, we found out in class that the capacitor acts as a EMF source. Okay, so if you remove the EMF source and basically just replace the EMF source with just another wire, the capacitor becomes its own EMF source, and then we get a circuit. All right, so it's going to look something like this. Okay, so right here is where the EMF source was, but I'm going to replace it with just a wire, right? And here we have a resistor R, and here we have a capacitor like so. All right. And also very important to note that the left plate was positive when we charged it up, and the left plate was negative. Okay, so we're going to do the same loop rule, but we are going to look at it in a clockwise fashion. Now, here's a couple important things. This is the conceptual idea behind the math. So we always know that the current flows from positive to negative. So what that means is that before the current was clockwise, but you can see here, positive to negative, the current will be counterclockwise. Okay, and this is important when we come up with Kirchhoff's loop rule, because that designates the path of, or the signs when we create the EMF formula. All right, now because the capacitor is not an actual EMF, the voltage will approach zero. Okay, so let's come up with those rules first. The rules are at time of 0 seconds, okay, we have Q initial, which is basically going to be Q max, which I'm going to just write as capital Q, because this is the total amount of charge that can be on the capacitor. Okay, and at this point, we also have the delta V max, okay, where this delta V will be equal to the EMF because well, it acts out like the battery. And we also know the formula for capacitance is Q over V, and when we charged it up, that V was just the EMF source. All right, and so as time continues, we say just time is turning into t as in time, we know that the charge on the capacitor decreases. And so we can say that the Q is less than the Q initial. Okay, so the amount of charge on the capacitor decreases. And we're just going to be using the variable Q to designate how much charge is on there. Now, in terms of our formula, this Q, the amount of charge, we'll write it as a function of Q of t, like so. All right? So with that being said, let's come up with the Kirchhoff's loop rule. Okay, we're going to start here in the lower left-hand corner, and the first thing that we're going to hit is that resistor. And so we have negative IR, and then we go from positive right here, this positive plate, and because we're going from positive to a negative, we have a drop in EMF. And so we have a negative EMF of a capacitor, and oops, the formula for the capacitance, you can see right there. And so we can replace that with Q over C as the EMF. And because there's nothing else in the circuit, if we go back to the start of the loop, we can say it's going to reach 0. All right, so now that we have our EMF formula, from there what we can do is we can create a differential equation, and from that differential equation, we can actually solve for the amount of charge on the capacitor with respect to time. So as a reminder, lowercase I is the changing current. Remember, in calculus, we use lowercase letters to show that the variable is not a constant or is a variable, and we know that to be dq over dt. So let's start off with that. We have negative dq over dt is equal to, I'm just moving the q over c onto the other side. Now, if you remember from the last video, the next thing that we want to do, oops, there should be an R right there. The next thing that we want to do is we want to rearrange this formula so we have all of the like terms together. And specifically, because we're creating a function for charge, I want to make my Q's or my DQs on the left-hand side. Okay, and so what we get is DQ over Q. Okay, I'm gonna move that negative and the R over to the other side. We get DT over negative RC. All right, and at that point, the only thing that we have left is to actually create our integrals and their bounds. So let's create our bounds over here. Right? So at time of 0 seconds, we know that we have Q max, okay, which I'm just going to write it as Q initial to save time. And as time approaches infinity, we know that time passes, so I'm just going to write that as T for time. Okay, and we know that the charge can be just written as Q, or the amount of charge left. All right, so we integrate both sides. Let's set our bounds. So this will be 0 seconds, and this will be just T. Excuse me. This should be charge. So this should be Q initial for Q max and some amount of Q later. And over here we have T 0 seconds, and here we just have T of T seconds there. So when we take the integral of both sides, we get the natural log of Q, and our bounds are Q initial and just Q, as in Q final, which is equal to negative 1 over C, and then we get T minus 0, so I'm just going to write that as T, like so. Okay, now let's just clean this up a little bit. I'm going to put in my bounds after I integrate, so we get the natural log of Q minus the natural log of Q naught. And we will be using the natural log rules there to combine on the next line down. So we get Q over Q naught is equal to negative T over RC. And already, hopefully, you're seeing the derivation taking shape to the function that we want. All right, I'm going to get rid of that natural log by raising everything e to the power of. And so we get Q over Q naught is equal to e to the negative T over RC. And so our function, Q of T, therefore, is equal to Q naught e to the negative T over RC. So we got to the final derivation, which is fantastic. All right, so the other thing that we need to be able to do is we need to be able to create like a charge versus time, a current versus time, and a EMF over time. So let's do that. Let's actually split it apart. Okay, so let's do the charging up first. So this is charging up, and then we will do discharge right next to it. All right, this is charging up, and this is discharge. So let's do Q with respect to T, Q with respect to T. So we know that in the beginning, the capacitor has no charge, and as it charges up, it reaches a max charge. Okay, so the line looks like this. Very good. And the max value for the single resistor and the single capacitor, this would be Q max, right? Which we found to be CE. Now, the CE comes from the formula. So if you remember the formula for the charging up, it gives us QT is equal to C EMF 1 minus e to the negative t to the RC power, right? And so the maximum is right there, is the maximum value. Okay, and this concave down shape comes from this middle part of the function right here. All right. Now, for a discharge, okay, we start off with maximum amount of charge. So we're going to start that up there. And over time, it's going to approach to be no charge. And once again, this is going to be CE or Qmax, okay, depending on the charging up shape. And this concave up shape comes from our function of e to the negative t RC. Okay, that you can see right there. So what I just highlighted in yellow gives us the shape, and the amplitude is that Q naught right there. Okay, so that gives us our max value. All right, and now we have current versus time. Okay, current versus time. And just so you know, if they ever give you a charge function to go from current versus time to charge versus time versus the current, all you gotta do is take the derivative. So the first derivative of charge with respect to time gives us current, okay, with respect to time. All right, so we know that in the beginning, the amount of current that's flowing is at a max, okay, and over time, as the capacitor is being filled to the brim, the current slows down to be a zero. And this max current, it will be, according to Ohm's law, V equals IR. So V is equal to, which is equal to I max. Okay, and we know that because in the beginning the capacitor acts like a wire, right? There's no reverse or back EMF happening there. Now on the flip side, the I versus time, the amount of current that is flowing, okay, we have maximum amount of current in the very, very beginning, and that quickly goes to zero, okay? And we know that it follows this shape simply because at the beginning we had a lot of charge to push out, and as time continues, there's less and less charge being pushed out, right? And this max current, of course, is going to be E over R based on the EMF that we charged up the capacitor with. All right, the very last graph, which will be a voltage time graph. Okay, so for the voltage time graph, this is the amount of volts or the potential difference for the capacitor. Now, just as a reminder, so as more Q, right, as more charges build up in the capacitor, more voltage or more potential difference is created. So the way that I like to think about it is we always describe voltage as just like analogous to like height, right? And so imagine that we have like a cup, okay, and then we try to fill up that cup with water. So in the beginning, there's no water there. So at time of 0 seconds, there's no water. So your Q is 0, okay? And also the water height is at a 0, okay? So 0 volts. But as we add water, okay, let's make that a little bit brighter. Can we do that? No. All right, so let's fill in this cup. There we go. All right, so that's empty space so that my highlighter shows. right? So as we add more and more water, okay, the water height increases, and that water height is just like the voltage. So as time continues from t0 seconds to t of t seconds, okay, the amount of charge increases. Therefore, the voltage, or the delta V, also increases. Okay, so remember, voltage is like so that will be like the change in water height. So in the beginning, when we are charging up the capacitor, there's no charges there, so there's no voltage, and then just sort of flattens out like this, okay? Where for the capacitor, the max voltage, as long as it's just a simple resistor and a simple EMF source, this will be equal to the EMF source. And in class, we'll look at the different scenarios. And for a discharge, okay, we start off with a maximum voltage. So this is just the EMF, and it quickly dies down to 0. Okay, so 0 volts. All right. The only other thing that I want to talk about is the time constant tau. So one of the things that you'll recognize is that in both formulas, we have, let's take a look at the very beginning. We have this negative t over RC, negative t over RC. And so what that describes is what we call the time constant. So the time constant which in this case represents tau, is, I guess, like how long or how long slash quickly the capacitor fills up or discharges, okay? And it's dependent on two variables, the resistor within the circuit and the amount that the capacitor can actually hold, the capacitance, okay? And so the important thing about tau is that it's actually divided up into fifths. The fifths are described like this. Well, before we actually describe that, let's give you the formula for the time constant, which is just RC. Okay, so the time constant for a charge up, okay, is determined by 63.2% of the capacitor must be charged, and for a discharge, that number is 36.8% amount of the capacitor is discharged. So a time constant, or a tau, of 1 for charging up means that the capacitor is 63.2% of the way charged up, and a time constant of tau 1 for discharge means that 36.8% of the capacitor has discharged. Now we're going to look at the relationships between tau, R, and C in a little bit so that we can make a little bit more sense of it. But let me just show you in terms of QT where these numbers come from. So the first thing I'm going to do, let's do a charge up. Okay, so we have 1 tau here. We can call this 2 tau and 3 tau, 4 tau, and 5 tau. Okay, and so what that shows you is that 1 tau right here, it is at a 63% of Q max. Okay. Versus a discharge scenario. So discharge looks like this, right? So that's a discharge, and tau 1 right there would be, this is equal to 36.8% has discharged. Okay, so that's the tau 1 for both scenarios. Represents different things, but the formula for tau is the same, RC. So let's take a look at the relationship between tau and R and C. Okay, so tau, the time constant, RC. So we know that if the resistor increases, okay, the time constant will also increase, the directly proportional. And we got to think about it, because what this tells us is stronger resistor, okay, overall the current will decrease according to Ohm's law, right? V equals IR. So if this goes up, I has to go down, right? Which means that the capacitor charges up slower. Okay, so the idea is that tau is how long it takes. So the tau, or the time to charge, increases. Okay, the inverse is also true. Now, what about tau and RC? Right, so tau and C are also directly proportional. So C, or capacitance, is how much charge it can hold, right? So we know that capacitance, the formula for capacitance is Q over delta V, so it's a ratio. And the way that I like to think about it is if we're using the water cup analogy, right? So let's just do a cup of this size, right? So this is our delta V, and versus a similar cup, but very, very thin, like so. So the delta V's are the same, okay? But remember, charge is like water, right? So I'm gonna color this in so that the highlighter shows, okay? So if we were to like turn on the water and try to fill that cup, because this has so much more volume, okay? Or volume, or the amount of space, that would be like the capacitance, right? It can hold more. Because it can hold more charge, it'll fill up a lot slower, okay? And so here, because C increases, the tau also increases, okay? The time to fill increases. Versus if you have like a nice and skinny cup, right? If you turn on the faucet, it's gonna fill up really quickly. And that's because for here, if the capacitance goes down, or the amount of charge it can hold goes down, in this case, I described it like volume, the time that it takes to fill up will also go down. All right, and that is that. I'll see you all next time. Bye-bye.